Okay, so this is our third and final lecture for Chapter 4 over fibers and textiles. So today we're going to be looking at how we can use fibers in forensic science. So by the end of this lecture, you should be able to distinguish between direct and secondary transfer of evidence, apply forensic science techniques to analyze fibers, describe several different techniques used to locate and collect fiber evidence from a crime scene, discuss how the use of technology has improved fiber examination, describe some methods of examining fibers that result in destroying the fibers, and describe different physical characteristics of fibers and fabrics used to identify them. There are a couple of vocabulary terms that you will need to be familiar with. So this involves direct transfer, secondary transfer, polarizing light microscopy, infrared spectroscopy, ultraviolet light analysis, burn testing, and solubility testing. So fibers are used in forensic science to create a link between the crime and a suspect. Collecting these fibers within 24 hours is critical to the investigation. Fibers are not specific to a single person, so this means that fibers are considered a form of class evidence. They are also a form of trace evidence. So fibers can be left behind by direct transfer or secondary transfer. So let's look at the difference between these two. So direct transfer is when fibers are transferred directly to a victim or suspect from the original source. So these fibers may come from carpets, clothing, linens, furniture, insulation, or rope. So for example, carpet to the victim, or from the victim to a suspect. So if a victim walks along carpet and those fibers are left on their shoes, that is an example of direct transfer. If a victim brushes up on a suspect and fibers from their clothing is left on the suspect, that's also considered direct transfer. Secondary transfer is when fibers are transferred from the original source to a victim and then to a suspect, or vice versa. So fiber transfer depends on the duration of contact, the type of contact, and the type of fiber, just like in Locard's principle of exchange. So for example, if fibers from carpet are transferred to a victim and then from the victim to a suspect. So let's look at how we can collect fiber evidence at a crime scene. Fiber evidence may be recovered from rugs, blankets, furniture, clothing, cars, household objects such as screens or windows, or even wounds. Fiber evidence can be collected using tape, forceps, or a vacuum, or even a lint roller. So once fibers are located at a crime scene, they need to be individually removed. They can then be placed on clean paper and sealed in evidence bags. The entire article of clothing or other textile from which the fiber was obtained is then rolled inside paper and sealed in an evidence bag. Large objects such as screens or car fenders are boxed, sealed, and sent to the crime lab. So once we have these fibers, there are a couple of different things that we need to evaluate and consider when linking these fibers to a crime or to a suspect. So the value of fiber evidence in a crime investigation depends on its potential uniqueness. So first of all, we have the type of fiber. What is the composition of the fiber? And how common or rare is it? What suspects or victims or parts of the crime scene had this type of fiber? You also need to consider fiber color. Do the fibers from the suspect's clothes match the color found in the victim's house? Is the type of dye the same? Number of fibers found. So how many fibers were found? One or hundreds? More fibers suggest violence or a longer period of contact. The location the fiber is found. So where was it found? How close can you place the suspect to the scene of the crime? Were they in the house or were they close to a victim's body? The value of fiber evidence in a crime investigation also depends on the textile the fiber originated from. So are these carpet fibers or upholstery from a car? Multiple fiber transfers. Is there only one type of fiber transferred at the crime scene, or are there fibers from numerous sources, from carpet and clothes and bedding? More sources suggest longer contact or possible violence. What is the type of crime committed? Was it a violent crime, a breaking and entering, or a kidnapping? Each type of crime has an expected pattern of contact among suspect, victim, and crime scene that will be reflected in the transfer of fibers. And last, time between crime and discovery of fiber. So how long ago did the transfer take place? Was it an hour ago, a day, a week? Unless the fiber location is undisturbed, such as a bagged jacket or locked room, the value of found fiber is greatly reduced with the passage of time because fibers not related to the crime can be picked up. Okay, so the first thing that we do as forensic scientists to examine these fibers is we look at them under the microscope. And this image shows different types of fibers and what they may look like under the microscope. So the first one I want to focus on is this nylon polyester. It will be circular, uniform in diameter, clean cut. So that is what polyester and nylon will look like under a microscope. Flax, which comes from the stems of plants, is going to be polygonal, meaning there's a polygon shape. It also has a lumen, which is this little center of the fiber itself. Wool will be either oval or round, and then it'll have those overlapping scales that we know as the imbricate cuticle of wool or sheep hair. Cotton is going to be more flat and oval. It also has a lumen, which is going to be that open space in the center. So again, this black portion here. And then it will have convolutions, which gives cotton a twisted or spiraled appearance under the microscope. Rayon, which is another example of a synthetic fiber, will be more circular. It will also be serrated and have lengthwise striations. Silk is going to look different under the microscope as well. So it's going to be more triangular with slightly rounded edges. And this shape of silk gives it the shiny appearance. And then another type of nylon can be trilobal, which will also give it a little bit of a shine. So once we have these fibers and we've looked at them under the microscope, if we still can't determine exactly what type of fibers they are, or if we want to compare two different types of fibers, we have different techniques that we can use. So there are a couple of techniques that do not destroy the fiber: polarizing light microscopy, infrared spectroscopy, and ultraviolet light analysis. However, some testing does destroy the fiber, but can give us some really good information on the composition of that fiber. This is burn testing and solubility testing. So let's start with polarizing light microscopy. This type of microscopy uses a microscope with a special filter that allows scientists to look at the fiber using specific light wavelengths. So here's an image of two different strands of cotton. Both of them have the spiraled appearance, but they have different wavelengths or different colors that reflect from them, meaning they're two pieces of cotton that came from different sources. Here is another image of cotton fibers, and it's just a little bit closer, but this one shows that these fibers all reflect similar colors of light, similar wavelengths of light, and are more likely going to be from the same source. Infrared spectroscopy is really interesting. This emits a beam of light that bounces off the material and returns to the instrument. How this beam has changed reveals characteristics of the chemical structure of the fiber. So what are the different types of chemical groups that make up this type of fiber? So in this graph here, we have the different types of fibers and then the characteristic absorbance bands, which you will see in the next couple of slides. So for cotton, you will see these different bands at these absorbencies. For wool, it will be these, silk, so on and so forth. So let's look at those. Here is a graph that was created when we did an infrared spectroscopy on cotton. So these are the absorbency bands that we're talking about. So different types of fibers are going to have different infrared spectroscopy graphs. So here's wool, which is definitely different than cotton, right? Here is silk, which is kind of similar to wool and cotton. Here's polyester, and this is a synthetic fiber, so it has a very different infrared spectroscopy. Right? There's not really those large bands over here that we had with the natural fibers. And then here's nylon, which has the bands in this area, but they're much smaller. Okay, so ultraviolet light analysis. When shining a black light or a UV light on fibers, the light can be re-emitted at a lower and more visible wavelength, giving different fibers unique characteristic glows. So this fiber may not have been spotted without the ultraviolet light. Okay, so now let's look at burn testing. And again, this is a type of testing that ultimately destroys the fiber. Burn testing involves using heat to test different characteristics of a fiber or fabric, including the temperature at which it burns, the smell of the fabric as it burns, and the ashes left behind. So here is the fabric burn guide for natural fabrics. So if the fabric burns completely and it has an odor of burning grass and gray ash, then it is linen. If it burns completely but has an odor of burning paper and still leaves behind a gray ash, then this would be cotton. So cotton and linen are going to have very similar effects, but the odor is what can tell you the difference between the two. Now, if the fabric burns briefly and then goes out, and it will probably have an odor of burning hair, but leaves behind a dark ash, then that would be wool. If it leaves behind black ash, then you know it is silk. So let's look at the burn guide for synthetic fabrics. So again, if it burns completely, has an odor of burning paper and leaves behind gray ash, then it is rayon. If it burns completely and has an odor of burning meat and leaves behind black char, then it is acrylic. If it burns briefly and then goes out, has an odor of sweet chemicals, leaves behind a gray char, it is nylon, or leaves behind black char, it's polyester. Solubility testing involves attempting to dissolve fibers in various solvents such as acetic acid, acetone, hydrochloric acid, sulfuric acid, and zinc chloride. So this type of test is particularly important for distinguishing between different types of synthetic fibers because there are less microscopic variations. So you can see the different types of solvents that these fibers will dissolve in.